By moving less computationally intensive jobs to different parts of the architecture, it is possible to offload some work from centralized cloud computing in the world of data centers with wings and wheels. Today's video is about edge computing in 8 minutes. The concept of having computational infrastructure located closer to the origin of data is referred to as having an edge. It is the distributed framework in which data is processed in a manner that is as close as feasible to the data source from where it originated. For this infrastructure to function well, it is necessary to make efficient use of resources like computers, cell phones, tablets, and sensors that are not always linked to a network. Edge computing encompasses a wide variety of technologies such as wireless sensor networks, cooperative distributed peer-to-peer ad hoc networking and processing, which can also be categorized as local cloud/fog computing, mobile edge computing, distributed data storage and retrieval, autonomic self-healing networks, remote cloud services, augmented reality, and many more. Edge computing is also classifiable as local cloud/fog computing. The concept of cloud computing is anticipated to experience a period of decentralization. The concept of edge computing is based on the idea of locating computing, storage, and networking resources in closer proximity to the end user. However, why? Legit question. Why do we even require computing on the edge of the network? What benefits will coming into possession of this new infrastructure bring? Imagine a scenario in which a self-driving automobile continuously sends a live broadcast to centralized servers. In this scenario, the car would be driving itself. At this juncture, the automobile needs to make an important choice. If the car waits for the central servers to process the data and respond to it, the results could potentially be catastrophic. Even while techniques like YOLOv2 have helped to speed up the process of object detection, the latency still exists at the point in the system where the vehicle must first send data to the central server, then wait for a response from the server, and finally, take action. As a result, we need that fundamental processing, such as determining whether to stop or decelerate, to be done within the vehicle itself. By extending the capabilities of the public cloud closer to the edge of the network, edge computing aims to reduce latency as much as possible. This is something that can be accomplished in one of two ways: by using a proprietary software stack that emulates cloud services and running it on hardware that already exists, or by using the public cloud and smoothly extending it to numerous point-of-presence locations. The following are some compelling arguments in favor of utilizing edge computing. Privacy. For reasons of privacy, you should try to avoid storing and processing any raw data on cloud servers. Real-time responsiveness. The amount of time it takes to respond can at times be a deciding factor. Reliability. The reliability of the system is demonstrated by the fact that it is able to function even when unplugged from cloud servers. Eliminates a potential source of failure all by itself. Let's use the example of a device that responds to a hot keyword so that we may better comprehend the concepts that were presented earlier. Take Jarvis from Iron Man as an example. Imagine for a moment that your own personal Jarvis is transmitting all of your personal talks to a remote server so that they can be analyzed. Instead, it possesses the intelligence necessary to answer back when it is summoned. In the same breath, it is dependable and operate real-time time. Another example could be aerial vehicles such as drones or quadcopters. If we were to use these vehicles, for instance, to identify people or deliver aid packages, the machines would need to be intelligent enough to make fundamental decisions such as rerouting themselves to avoid obstacles in the immediate area. Different variations of edge computing equipment. Device edge. In this paradigm, edge computing is brought to the locations of the end users, who already have their own infrastructure. As an illustration, Amazon Web Services Greengrass and Microsoft Azure IoT Edge. Cloud Edge. This approach of computing on the edge is essentially an extension of the traditional cloud architecture. Classic instances of this topology include content delivery networks, in which static content is cached and provided across a geographically dispersed set of edge locations. One of the up-and-coming competitors in this space is Vapor.io. They are making an effort to construct the necessary infrastructure for Cloud Edge. Vapor.io offers a wide variety of goods, including the Vapor Chamber. These are monitored by the user themselves. The deployment and pricing strategies are the primary distinctions between the device edge and the cloud edge. There are a variety of different use cases that necessitate the deployment of these two models, device edge and cloud edge. It's possible that there will be instances when it will be beneficial to install both models. Edge examples of computing can be found more and more frequently around us. Smart street lights. The industrial equipment is fully automated. Mobile devices. Smart homes. Vehicles that drive themselves. The transmission of data comes at a high cost. By moving computation closer to the source of the data, latency may be cut down, and the overall experience for end users can be improved. Augmented reality or virtual reality and the Internet of Things are two of the emerging use cases for edge computing. For instance, the rush that consumers received while playing an augmented reality-based Pokemon game would not have been feasible if real-timeliness was absent from the game. The game would not have been able to provide the same experience. Because the smartphone, and not the central servers, was responsible for the augmented reality, this was made possible. Even more advanced forms of computing, such as machine learning, ML, can reap many benefits from edge computing. All of the intensive training of machine learning algorithms can be carried out in the cloud, and the resulting trained model can then be deployed on the edge for predictions in near real-time or even in real-time. We are able to observe that in the data-driven world of today, computing at the edge is quickly becoming an essential component of it. Edge computing and the Internet of Things are often confused with one another. In its most basic form, edge computing can be understood as nothing more than an intelligent version of the Internet of Things. Edge computing is an addition to the regular Internet of Things. The classic approach of the Internet of Things involves all of the devices, such as sensors, mobile phones, computers, and so on, being connected to a single server. Now, let's assume a scenario in which you give the command to your light to turn off. In order to complete such a basic task, data needs to be transported to the cloud, where it will be analyzed, and then the lamp will receive the signal to turn off. Edge computing brings computing closer to your house, which means that either the fog layer that is present between your lamp and the cloud servers or the lamp itself is intelligent enough to analyze the data. Benefits of edge computing. In the past 20 years, digital communication has made cloud computing and storage more accessible to the general population. Since cloud computing has limits, many have turned to edge computing as an alternative. Many businesses prefer edge computing solutions over cloud computing due to edge computing's superior response and latency times across applications and devices. Despite this, edge computing is used in healthcare, retail, manufacturing, and transportation. What do you think of our video? Let me know in the comments section below. Make sure you hit subscribe button and check my other videos about the latest tech in 2023 in the description below.